theoretically, if I was going to give you like a problem on a test that had to do with this, I might give you like a few graphs and be like, what's the parent function, right? So that first one is the square root function. And you could just give it in words. You don't even have to give like the equation for it. And that one is the cubic or cubing function, the squaring function, the absolute value function. So at this point, like that's as much as I want you guys to know. And then we'll get more into how these transformations happen with respect to what the function looks like as we get a little bit further into these different types. Cool? Okay, so let's talk 2.5. I printed these out again for you just because a bunch of graphs and words. You guys, I have to say, you guys have the best attendance and the best homework completion of all my sections. Rock stars. You got one. Oh, and Sam reminded me yesterday that I should mention to you guys, it's in the syllabus, but if you guys run out of tries on your My Math Lab, like you can always email me for more. So the reason I limit the number of tries is so that you don't like do a problem wrong 100 times and then get it right once, right? Because like probably what's going to stick with you isn't like that one time. So you have like 6 chances, and then if it's still wrong, like I would email me, and if you're not sure what you're doing wrong, I can help you with it and then give you another try. So you can always get 100% on your My Math Lab, and you can keep working on it up until the test. So if anything's under 100% and you want to bring it up, I can open it for you. You just have to send me an email.
Can I get one of those papers?
Oh yeah, I'm sorry.
Oh, it's probably my fault, actually. Sorry.
Oh.
Thanks.
Okay. So average rate of change. Let's look at something that's pretty familiar to all of us. Like suppose we're going on a trip. And let's say that our input is time and our output is distance. So we're not going to make like a formal function out of it, but just so we can think of it in terms of input and output. So after 0 hours, you've driven 0 miles. And let's say after 3 hours, you've driven 180 miles. So what we've looked at so far is net change, right? We've said that the net change in distance, and the reason we're looking for net change in distance is because distance is the output. So when we talk about net change, we're always talking about the output of the function. From hour 0 to hour 3 is just 180 minus 0, right? It's the output associated with hour 3 minus the output associated with hour 0. And remember that when we do net change, it's always the output associated with the bigger x value minus the output associated with the smaller x value. So when we had a worksheet last week. A lot of people are getting them mixed up. So you just want to make sure that you're doing, on a graph, it's like you're doing right minus left. So the bigger x value minus the smaller. doesn't matter what the values of y are. It's just the rightmost point minus the leftmost point. So which gives us 180 miles. So that's what we've done so far. We can say the net change in distance in those 3 hours is 180 miles. But it'd be more convenient if we knew like how fast we were going, right? Because then we could talk about like at any point along the journey instead of that entire chunk all at once. And so that's where this average rate of change comes in. It's similar to net change, except instead of over a period of 3 hours, we're going to just average it out so that we have a per hour distance change. So our average rate of change in distance from hour 0 to hour 3 is, so the numerator is going to be the same. It's that change in my y value. So my net change divided by the change in my input. So 3 minus 0. And that gives me 6, well, sorry, I should add units. This is in miles. This is in hours. So that gives me 60 miles per hour. And we call this average rate of change because likely over those 3 hours you weren't driving exactly 60 miles an hour the entire way, right? You probably went a little bit faster sometimes and a little bit slower, but if you average it all out, you get 60. So that's why we call it average rate of change. It's not like at any one moment along your journey, it's just the average of your speed over that 3 hours. So in general, let's look at the average rate of change of f of x from x equals a to x equals b. And we're going to assume that b is bigger than a. That way we'll get the order right. So the average rate of change is just the net change divided by the change in x. So net change divided by the change in x. So the net change is the function evaluated for your bigger x value minus the function evaluated for your smaller x value. And then the change in your x values is just b minus a. So notice the difference between f of b minus f of a and b minus a, right? F of b and f of a, those are y values. The y values that correspond to the x values of b and a, whereas b and a are x values. So it sort of looks like we have the same thing on the top and the bottom, but that function notation tells us that those in the numerator we have y values. So let's look at this graphically. Let's just say I have any old function. And we're looking at where x equals a and x equals b. So we've got 2 points. The x value of the first point is a, and then the y value is our function evaluated for an x value of a. So f of a is our y value. And then for our second point, we have an x value of b. And then again, our y value is just our function evaluated for that x value, so f of b. Now notice that, like, if you've worked with linear equations at all, right, we know that, like, straight lines have slopes. And we can't really say the same about curves because you can kind of see, like, towards the left of that curve, it's, like, shallower. It's less steep. And, like, towards the right, it's more steep. So it's like that whole thing doesn't have a slope because it changes steepness as it goes. And so we can't talk about how steep a function is or a graph is in general if it's not a straight line. But what we can do is take these 2 points and draw a straight line through them, and we call this a secant line. And a secant line is just any line that passes through 2 points on a graph. And the average rate of change is the slope of that secant line. So this average rate of change, if our function's not a straight line, notice that our average rate of change is totally dependent on which 2 points we choose, right? Because if I picked, like, say, this point and this point, there'd be a different line that passed through it, right? And so it has a different steepness. And so that's something we'll keep in mind as we, especially with application problems, when we write sentences to interpret these guys, that we have to mention which x values we used, because the points that our secant line is passing through totally determine what that average rate of change is. So there's a few different ways of viewing all this average rate of change stuff. And so I know it can get a little confusing sometimes to see so many different things, but we're just trying to relate the algebra to the graph to the applications so that regardless of how we're given the information, we can, like, fit it together to make sense. Is this good so far? Should we do a few? So we've got a graph here, and we want to find an estimate for the average rate of change of v between x equals 5 and x equals 7. So since we don't have an equation for the function, the first thing we have to do is just estimate the 2 points on the graph. So we have x equals 5 and x equals 7. I don't know, what do you think y is here? Oh, come on, don't make me do everything.
Can we just say 9?
Sure. What about the other one?
8. Or shape.
What?
Do 8.15.
Sure. So our average rate of change. Are you guys okay with me abbreviating that so we don't have to write out average rate of change every time? I'm okay with you doing that too. Is equal to, so our function evaluated at 7 minus our function evaluated at 5 over, whoa, that was wobbly, over 7 minus 5. So when I write v of 7, all that means is the y value of the point that has an x value of 7. So I look for where x is 7, the y value is 8.15. So v of 7 is 8.15. And then V of 5 is going to be 9. And then I always think it's a good idea with applications to include your units in the fraction, because then at the end you'll be able to get them right because you know what you're dividing by what. So what are we using to measure the y values? Millions of and then what are we using to measure the x values? Good. So we have negative 0.85 millions. I guess I don't have to say of million victims over 2 years. So right now, we have two separate numbers. We're saying that it's negative 0.85 million victims for every 2 years. In order to make this a rate of change, the idea of average rate of change is that it gives the change in your output corresponding to 1 unit change in your input. So we have to divide, and with applications, you can always just use a decimal. So 0.85 divided by 2, we get negative 0.425. So that's the numerical part, and then we need the units. You can think of division as like the word per. So we're dividing million victims by years. So our units are going to be million victims per year. Okay, what did we just figure out?
Every year,
Mm-hmm.
between the years of 2005 and 2007, the amount of identity theft victims went down 0.45.
Good.
0.25 billion or million.
That's perfect. In 2007. So remember we said that the average rate of change depends on which 2 points we choose. So that's why we're saying between 2005 and 2007 to show that those are the 2 points that we calculated this for. The number of fraud victims decreased 5.425 million per year. Oh, I made a mistake. I forgot a word. By an average of. 0.425 million per year. So there's a bit in there, right? Like there's a lot of information in this one statement. If you find that you're getting tripped up on these interpretations, like you can sort of literally make yourself a template for these. Like the things that you need are the two inputs, what your y values measure, either the word increase or decrease, the word average, the number, and then the units. So it would always go between something, well, let's just do a line, blank and blank the, I'll write that units for y. Either increased or decreased, you just choose one, by an average of blank, so the number, and then your units. So the wording's a little funky, but you guys get the drift, yeah? So like here, we put our X values in to those two blank. The units for Y were the number of fraud victims. It was negative, so we chose decrease by an average of, our rate of change was 0.425, and then the Y units is million victims, per X units is years. So far, so good? Okay, let's do this. I'm going to not do a, this one's a little redundant. Okay, so the only thing you really need to know about this one that makes it a little bit different is that speed is slightly different than the average rate of change in the function, in that this function measures height, right? So since she's falling down, her height is decreasing, so the average rate of change is going to be negative, but speed is always positive. That negative just tells us direction. So if you're asked for speed, regardless of the sign you get for your rate of change, you just give a positive speed. It'd be different if they asked for velocity, but I won't do that to you. I won't like mix it up. So anytime you see speed, you can make it positive, because speed is always positive. So let's start with our inputs. We are asked what her average speed was during the last 5 seconds before she opened her parachute. So what is the end of my time period? So if my time period is the last 5 seconds before she opened the chute, what ends that time period? When she opens the chute. So what time is that?
20.
When she opens it? 25, right? And then we want to start 5 seconds before that, which is what? 20, good. So we're finding the average rate of change between t equals 20 and t equals 25. So we have h of 25 minus h of 20 over 25 minus 20. Okay, go ahead and calculate that. If you want to figure out, like if you want to evaluate h of 25 like on the side and then plug it in, that's totally fine if you don't want to write it all in the fraction, if that is easier for you. We got 3,000 and 6,600. And this is in feet. This is in seconds. So if you use your calculator in that way, which is totally fine with me, make sure you're still writing this part of it. That way if you hit a wrong button or something silly like that, at least I can see that you set it up right. And I know it's just probably a typo. So we end up with negative 720 feet per second, which is like insane. It's like 400 miles per hour. like terminal velocity, I think, is like 230. So totally impossible, but. So speed. Average speed, I keep forgetting that word. In the last 5 seconds, was 720 feet per second. So I just dropped that negative because in this setting, the negative indicates that she's going down, that she's falling. And then the 720 feet per second is the actual speed at which she's falling. Any questions? Are we all good with like the difference between h of 25 and the number 25? They can look really similar, so we're all good that outputs, inputs. Awesome. Okay. So we're going to do this really quickly by having everybody from Lily over do A, and everybody to the right of Lily do B. Just like we did the last one. Okay, does anybody have an answer for A? Did you say 1/2?
2.
Yes. So this would be -1 minus -5 over 2. So that's 4/2, which is 2. Yep. What about B? 2. Which is interesting, right? Because we said that average rate of change depends on what points we choose. So let's try just 2 random points, like if x is A and B. So we want to do f of B minus f of A over B minus A. So f of B is just what I get when I put B into the function instead of x. So -3 plus 2b. And then f of A is just what I get if I replace x with A. So -3 plus 2a. over b minus a. Notice that I put those both in brackets because I want to, the first one you actually don't really need the brackets, but that second one you have to distribute the negative. So you need to put all of f of a in parentheses or brackets. You can use parentheses, I don't like brackets. So we're going to distribute negative 3 plus 2b plus 3 minus 2a over b minus a. Well, negative 3 plus 3 is 0, so that goes away. And I have 2b minus 2a over b minus a. And we haven't talked a lot about factoring yet, but if you look at the numerator, notice that the two terms both have a factor of 2. It's 2 times b minus 2 times a. And so we can kind of think of this as like doing the distributive property backwards. So this is the same as 2 times b minus a. Right, if you were to distribute that 2, you would get your 2b minus 2a over b minus a. But these are the same, so we can cancel them. And we get 2. Which means that no matter what two x values I use, I will always get an average rate of change of 2. And that's a property of what we call linear functions, which are functions that create a straight line. Because no matter what 2 points I pick on that straight line, the straight line through them is going to be the same, right? Whereas when we had a curve, if I picked different points, it gave me different secant lines. So the definition of a linear function is it's a function with a constant average rate of change, which just means that it's the same for all pairs of points. And it kind of goes both ways. If I know a function is linear, then I know that no matter what 2 points I choose, I'll get an average rate of change that's the same. But also, if I have a bunch of points and I want to know if my function is linear, then I can calculate the average rate of change between a few different pairs. And if it's always the same, then I know it's linear. The form, you've probably seen this before. The form for a linear function is f of x equals mx plus b. And like I said before, we want to connect this to the applications we're going to do and the graph and the algebra, right, so that we can move back and forth. So there's a couple ways we think of these numbers. The constant term, which is the term that doesn't have a variable, is the initial value of whatever the output is. On a graph, that corresponds to a y-intercept at 0b. And then m, which is the coefficient or the number being multiplied by the variable, that's our average rate of change. And in fact, because it's linear, we don't even need the word average because it's the same all the time. So we're not averaging it over a certain interval. It's always the same. And this is also known as the slope of the line. So you've probably seen this, the y equals mx plus b before. We just want to relate that to the applications that we're looking at. You guys got this? Okay. So for instance, we're told that the sea level of boiling, or at sea level, the boiling point of water is 212 degrees Fahrenheit. But as you climb in elevation, the boiling point decreases, and they give us the rate of decrease, and we want to find a linear function. So if we're finding a linear function, the first thing we want to know is what our inputs and outputs are, right? So it's x. X is our elevation. That's our input. And the reason I know it's an input, that x is my input, is because when they say find a linear function that models, the thing after the words that models is my output. So if my function is modeling the boiling point of water, then the boiling point of water is my output. And then it says at an elevation, so corresponding to an elevation of x feet. So that's how I know that x is my input. So my output is going to be b of x, and that's my boiling point. So whatever it is that the equation or the function gives you is what your output is. So now I have to look for one of two things. Either I need 2 points so that I can find the average rate of change, or they have to give me the average rate of change and an initial value. Do I have an initial value? Yeah, 212 corresponds to an elevation of 0. That's how I know that that's my y-intercept, or my initial value, because it corresponds to an input of 0. So b is equal to 212. And then when it comes to finding rate of change, look for units, right? On that 0.0018, it says degrees per foot. And so any units that have that slash or the word per in them, that's a really good indicator that that's a rate of change. So this is going to be my m. And always look for the word increases or decreases, because often they'll give it as a positive number, but then precede it with the direction it's going. So negative 0.0018. So my function is going to be b of x equals m, which is negative 0.0018 times x plus b. And that's all. So some of these, there's not a whole lot to do. You just have to kind of sift through the information to find what you're looking for. That is it for today. We